Welcome back to the series of lectures on high-performance scientific computing. So far in this course, we have had to be aware of the nature of the hardware on which we are trying to do parallel programming. For example, we were using OpenMP on shared memory machines which had multiple CPU cores. Similarly, when we went to MPI programming, we had to be aware that we were on a distributed network machine where we had to use communication to do parallel computing. Similarly, when we were doing GPU programming using CUDA, we had to be aware that there was a graphics card, and then we had to sort of explicitly write code that needed to be compiled separately for the GPU and then executed on the GPU. We also had to take care of transferring data from the host memory to the device memory and from the device memory back to the host memory. So now this brings a lot of complexity in terms of programming. Finally, we are interested in solving a scientific problem. Now, what if we have a scientific code which we want it to be a little bit agnostic? What do I mean by agnostic? When I write the code, I want it to run on multiple platforms. Now, the most common scenario is that you have a serial code and you want to accelerate the serial code. The easiest option that is there in front of you is that you can either accelerate it on a multi-core CPU machine or use a GPU. Well, we can always rewrite the entire algorithm and make it run on a distributed memory machine as well if you want to do extremely large-scale computing. But wouldn't it be nice to have a code where I can switch between multi-core CPUs and GPUs as and when I choose? Or the other way of putting these things is that I'm not aware to begin with whether I'm going to execute this code on a multi-core CPU or on a machine which has a GPU, the availability of which depends on the resources at that point of time. In such a scenario, it is better to use some programming paradigm which is a little bit agnostic. And today we'll talk about one of those. We're going to talk about OpenACC. OpenACC is something which is directive based. So, what is really OpenACC? It is a directive based programming approach for parallel computing where we look at the portability of code. So, what do I mean by portability of code? We write the same code, and based on how the compiler interprets the instructions given to it at compile time, you will be able to execute this code on different architectures. So, in short, you'll have the same code which is written, you'll have some simple compiler directives in it, and depending on the nature of the machine, it will either run on the CPU or onto GPU, giving you high performance. So, what are the different ways we have to accelerate applications? Now, we can obviously accelerate applications using libraries which are easier to use and probably give the most performance because they have been tuned. We will cover the use of certain popular libraries towards the end of this course. The second option is to use compiler directives. We have seen an example of that which is CPU specific with OpenMP. So this gives us easy to use sort of portable code. Obviously, if you want to have the maximum performance, you have to go deeper and specifically program it, and that gives you the most performance and also sort of the most flexibility in terms of getting it into the different computer hardware. So now let us describe a generic parallel machine on which the OpenACC portability is designed. So typically, we have studied this in CUDA. You have a host where the main code runs. The host has its own specific memory, and then you have a device, and the device has its own specific memory. And then you sort of copy and do data transfers between the host and the device memory. This is the most generic way of symbolizing such a parallel machine. Now, The way OpenACC is designed, it is that it is designed to be portable across many existing and also upcoming future platforms. The one advantage that OpenACC gives you is that you do not need to think about the hardware specific details. I would rather have the expression of the parallelism in very generic terms in the code. So an OpenACC program, very similar to a CUDA program, ideologically runs on a host, which is typically a CPU, but then manages one or more parallel devices. Now, this could be GPUs, it could be multi-core CPUs, so on and so forth. The host and device are logically thought to having as separate memories. In actual realization, they might have common memories, but there is some sort of a demarcation in the ideology on how we use this. What are the advantages of OpenACC? First of all, what development that we do with the code is sort of incremental. We always are working with a single source code. What I'm trying to say over here is that if you want to run the code in serial, you go back to the same code. If you want to run the code in parallel over multiple CPU cores, you go back to the same code. And similarly, if you want to run the GPU version of the code, you're still using the same code. So if you have a single source, then the chances of putting in errors into the code actually becomes 1/3, because now you're working only with one version of the code, rather than implementing the same algorithm across 3 separate codes. The other big advantage of OpenACC that it has a very low learning curve. That means it is very easy to pick up how to parallelize using OpenACC and implement the parallelism. So let's talk about the incremental nature. So what typically research groups have is that they maintain an existing sequential code, and you can continue maintaining this sequential code, and you're just making some very minor modifications to it. You basically add annotations to expose where you would like to have the parallelism or express the parallelism in the code. And then you verify the correctness, and as you keep working on it, you annotate more and more bits of the code. So typically research codes are several thousands lines long. You can start off by parallelizing some parts of it and then incrementally increase the amount of parallelism in the code. So what do you essentially do? So you begin with a sequential code. So for example, you would have some code structure like this, which runs over a loop. Then you parallelize it with OpenACC by identifying these loops and putting these directives in front of these loops. Very similar to OpenMP. You then rerun the code to verify the correct behavior. You can keep changing or altering the OpenACC code as long as you want to verify the correctness. So as I said, the advantage of this is that you work with a single source. So that means I can use the same code to rebuild it on multiple architectures. The compiler actually determines underneath how to parallelize on a desired machine. In the previous examples, we had seen that for OpenMP, we had to do one set of things. For CUDA, we had to do another set of things. In fact, for CUDA, we had to rewrite a whole lot of code to use the GPU correctly. Here, the compiler will determine how to parallelize it on a desired machine. So the next natural question is, what are the different architectures that are supported by OpenACC? So you have all these sort of CPUs and GPUs which are now supported by OpenACC. Obviously, the list is not exhaustive, and in the future there could be newer architectures which would come for which support would need to be added. But today, if you look at it, the most popular architectures like Power, x86, x86 Xeon Phi, NVIDIA, so on and so forth, are covered in this. And you basically are maintaining the sequential code, and if you were to take away the compiler flags, then you have essentially gone back to a code which is verifiable and is serial in nature. So for example, if you have a code like this, I can put in the directive. The compiler can be given an option to ignore the OpenACC code additions so that you can use the same code for both parallel and serial execution. This comes to the last point of this, that the OpenACC essentially means that you have a low learning curve. You do not have to work very hard to parallelize the code using OpenACC. It is meant to be easy to use and easy to learn. The programmer still maintains a very familiar structure of C, C++, or Fortran, whatever their choice of programming language is. And obviously, there is really no need for the programmer to know the lower level details of the hardware which is there. So effectively, what you're going to have is that you're going to have some sequential part of the code, then you're going to have the OpenACC directives, which is going to now expose the code to some parallelism on the underlying hardware, which the programmer initially is agnostic about. It is only decided at the runtime. So you'll have a CPU which runs the sequential code, then the parallel code is exposed using a compiler hint, which is the directive, and then the programmer will give different hints to the compiler about which sections of the code are needed to parallelize. The parallelism will be generated by the compiler for the particular target hardware. As I said, the target hardware could be different based on what machine you are. You then are executing this parallel code on the said parallel hardware. The parallel hardware, as I said earlier, could be multiple CPU cores, could be a GPU, or could be anything. So these are sort of the advantages of OpenACC. So where you have an incremental way of approaching the parallelism, where you work with a single source, and then you have a lower learning curve. There are several OpenACC resources which is linked over here. You can go to this particular website. The one thing that is important for implementing OpenACC is that your compiler needs to support OpenACC. So there are free compilers which allow you to have OpenACC support, GCC and PGI being the two most popular ones. So how do I now start expressing parallelism with OpenACC? Let's look at this simple example of pairing, where I loop through an array which is n long, and I say output I is equal to input I into 2 plus input I into 2 plus 1. So essentially what we are doing is that assuming that this is the input array, which is about like 10 elements long, you then, or rather 12 elements long, you then compute the output array by taking the sum of every 2 elements. For example, the first entry in the output array will be 9, which is 6 plus 3. The second element would be 17, which is 10 plus 7. Then you have 6, you have 11, you have 11 again, and then finally 1. So if I were to do this in parallel, then if I had 2 processors, I could do it in a multi-threaded way by looking at it in this form. So one thread could compute the first 2, the second thread the third and fourth elements. Similarly, I could go ahead, compute 6 and 11, 11 and 1. So if I put the OpenACC parallel loop, we can think about doing this in one shot as well. Now, if we have certain data dependencies, then we are in a little bit of a problem. Let us say that we have a loop of this sort where AI is equal to AI plus AI minus 1. Now, if I have the same input array, and let's say it is sequentially numbered 1 to 10, let's say we have an array where the index is the input data, and if we want to execute this, in the first counter of the loop, the second element will be modified to 3. Then the third element will be modified to 6, go to 10. In the fourth iteration, it will become 15. Fifth iteration will become 21. Sixth iteration will be 28. Seventh iteration will be 36. Eighth iteration 45. And ninth iteration finally 55. Now, if I were to do this in parallel, what would the problem I face? Now, this is the output from a sequential run of this code. Now, if I want to do a parallel implementation, we would get wrong answers because there's a forward dependency over here. So let us assume that we are taking two threads and we are operating with the two threads in parallel, where each thread is operating on alternate indices. The first thread is operating on 1, the second thread is operating on 2. In this case, in the first iteration, or rather the first two iterations which are run in parallel, what will happen is that iteration I will get it correct, I is equal to 1 will get it correct to the answer 3, but because we do not have the updated value of I is equal to 2, you're going to get a wrong answer for the third entry into the parallel array. Similarly, from there on in, you're going to keep getting wrong answers because you have had wrong inputs now. So you would end up with only one correct result and the rest of it is going to be wrong. Now, there's another way to parallelize this, where instead of picking just alternate indices, I could split the array into two and then do the computation. As in, like I take the first half of the array for one processor and the other half of the array for the other processor. In that case, for the first iteration, one thread will do I is equal to 1, the other thread will do I is equal to 6. I is equal to 1 is going to get it right, but I is equal to 6 is going to get it wrong because you have not updated the sixth element. Similarly, when you go through the iterations, what you're going to see is that the first half of the array is going to result with correct answers, but the second half of the array is going to end up with incorrect answers. So this is something which we really need to take care of when we are doing directive-based programming. We have to really take care of the data dependencies. We had seen the same sort of issues when we were doing OpenMP programming as well. In the next video, we will now see a little bit more of intricacies of OpenACC programming. Thank you.